Hello! In this lesson we will learn about rigid motions, also known as isometric transformations. The learning goals are to learn how to perform rigid/isometric transformations, specifically translation, rotation, and reflection, and also to learn how to express isometric transformations as functions. A transformation is a change of size, orientation, or position of an image. For example, here we have a triangle ABC. That will be our pre-image, which is the figure before the transformation. In this example, we will translate that triangle into a different position. So we generate an image, which is the figure after the transformation. We always label the image with the same letters as the pre-image, but we add the prime symbol. In this example, A prime, B prime, C prime. An isometric /rigid transformation, or isometry, is a transformation where the pre-image and the image are congruent. There are three types: translation, reflection, and rotation. In this animation, we can see how they change according to their respective transformation. A translation is when we slide a figure in any direction. A reflection is when we flip a figure over a line. And a rotation is when the object or figure is turned around a fixed point. Let's start explaining more in detail what translations are. For this example, we start with a blue trapezoid, which is going to be translated to the position of the yellow trapezoid. And we want to describe the rules of this translation. To do that, we're going to mark the blue trapezoid with 1 point in one corner, and we will mark the yellow trapezoid with a point in the same or the corresponding corner, so we can track the motion. So this is the movement that is going to happen for the blue trapezoid to be in the same position as the yellow trapezoid. Basically, what we're doing is we're moving this point here as a reference: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 positions to the right, and 1, 2, 3, 4, 5, 6. 6 positions down. So the rule would be that we start with a coordinate x, y. We're going to add 10 to the x, and we're going to subtract 6 to the y. The plus 10 indicates 10 positions to the right, and the minus 6 is because it goes 6 positions down. Another way to find the rule of this translation is just to find the change in these two coordinates here. So let's label them. This is -8 for the x, 2 for the y, and this coordinate is 2 for the x, -4 for the y. So we're going to put one coordinate on top of the other. We're going to find the difference between these two x's and the difference between these two y's. So we're going to say 2 minus negative 8 is the difference between these two x's. 2 minus negative 8 is the same as 2 plus 8, which is 10. And for the y, it will be negative 4 minus 2, which is negative 6. Therefore, we arrive at the same rule, that the x increases in 10 and the y we subtract 6. So those are two different ways to find the rules of this translation. Now let's describe translation as a function. A translation is a function t which takes as its input a set of pre-image points and outputs a set of image points. Let's explain this in more detail. Let's say that they give us these graphs here with the points P, P prime, and P double prime, and this segment here with the points A, B, and C. And then they give us this function, this translation function. P, the point P, is going to be the input of the function. The point P prime is going to be the output of the function. AB is the direction and distance that the point P is going to move. So P is going to move in this direction, in the same direction from A to B, and the same distance as the distance from A to B. And that will create the point P prime. So translating point P into the direction of A to B gets you to point P prime. That's how you will read this function here. Let's see another example. Here, this would be read as we're translating the point P into the direction A to C, and we get to point P double prime. Okay? So this part here is the direction and the distance. This is the input, the starting point or the pre-image, and this is the output, is the endpoint or the image. In this example, we're going to translate the sun using A towards B as a reference, right? So what we do is first we establish the direction and distance from A to B. We draw a parallel line or segment here on the sun, and the sun will move like that. So the sun is moving in a parallel trajectory to A, B. And we label this as prime, saying here, because remember, before the translation, we have a pre-image, and after the translation, the image is always labeled with a prime symbol, same as here. Now, let's go into reflections. Again, we start with an example. The blue parallelogram is reflected across the line shown here, this red line. We have to find the coordinates of its reflection. So to find the coordinates of the reflection, what we do is we say this coordinate, this vertex, has a distance of 1, 2, 3 towards the red line. So the reflected point of this vertex is going to have the same distance, 1, 2, 3, but on the other side of the line. Same thing for this vertex here. It has a distance of 1 towards the line, so the reflected point will have a distance of 1 towards that line. So saying this distance from this vertex to the line will be the same distance from this vertex to this line. And this distance here will be the same as this one. So basically the red line is in the middle between the points of the blue parallelogram and its reflection. So this is -2 for the x and -2 for the y. This is -4 for the x and -2 for the y. This is -1 for the x, -4 for the y, and this coordinate is -3 for the x, -4 for the y. Now let's go and describe the reflection as a function. A reflection is a function, Rm, that transforms a figure, the input or pre-image, into a new figure, the output of the image, by mirroring it across a line of reflection, M. Here we have point P, and we have the line M. So this function here will reflect the point P across the line M and generate a point P prime. So this distance from point P towards the line M will be the same distance from the line M towards the reflected point P prime. To reflect a figure, for example a triangle, will reflect all of its points across the line of reflection. In this example, we have a triangle ABC, and this function will read as this. We're going to reflect across the y-axis the triangle ABC. Just like the animation shows, we're flipping the triangle or reflecting it across the y-axis. And we generate a triangle A prime, B prime, C prime. So ABC, this triangle is our pre-image, A prime, B prime, C prime. This triangle here is our image. And the y-axis is in the middle between these two triangles. So the distance between A and A, so basically the distance between the line, the y-axis, and A is the same as the y-axis and A prime. The distance between B and the y-axis is the same as the distance between B prime and the y-axis. And the distance between C and the y-axis is the same as the distance between C prime and the y-axis. Okay, so now we're going to go into rotations. A rotation is a function in which an object, like this blue square, is rotated around a fixed point, which is going to be the center of rotation. The distance of an object to the center of rotation is called the radius of rotation. So that distance would be the radius of rotation. So we see how the object gets rotated around this center of rotation. the amount of rotation made is called the angle of rotation. Now, let's illustrate rotations with this triangle here. We have this triangle ABC. We label the vertices. The center of rotation would be the origin, the 0, 0 point. And we are drawing a segment between the center of rotation and coordinate A as a reference. So the coordinates for this triangle can be represented by x, y. We're going to rotate 90 degrees. Just remember that whenever we rotate a positive angle, the rotation is counterclockwise. Okay? So we're going to rotate this triangle 90 degrees. Like that. Now, the coordinates for this triangle after the rotation are A prime, -2, 1, B prime, -2, 3, and C prime, -4, 1. Now, if we compare these coordinates here, A and A prime, we realize that we are basically switching these numbers. Here the x is 1 and the y is 2. Here the x is -2 and the y is 1. Yes, this is negative, but basically we flip these two numbers and we make this coordinate negative. For the b's is the same thing. Here we have 3, 2. Here we're flipping the 3 and the 2, so it will be 2, 3, and we make this coordinate negative. And same for the C prime. You see in C is 1, 4, and in C prime is -4, 1. Again, we flip these two and we make this coordinate negative. So the rule is that after a 90-degree rotation around the origin, the coordinates are going to be -y, x. So if here the coordinate in the first quadrant is x, y, the coordinate after a 90-degree rotation is going to be -y, x. Again, we switch the x and the y's and we make this coordinate negative. Now, we're going to rotate 180 degrees this blue triangle. Basically 90 extra degrees here. So we have a full 180-degree rotation. And we're going to label the coordinates A double prime, B double prime, and C double prime. And we're going to compare those coordinates with the original ones. So we see here that when A is 1, 2, A double prime is -1, -2. When B is 3, 2, the B double prime is -3, -2. So what we're seeing here is that we use the same numbers, but we make both of them negative. The A is 1, 2, here is -1, -2. The B here is 3, 2, so the B here is -3, -2. And the C here is 1, 4, and the C here is -1, -4. So what we see here basically is that the rule will be we use the same numbers while we make both of them negative as compared with this coordinate here in the first quadrant after we rotate 180 degrees around the origin. So now we're going to rotate 90 extra degrees to get 270 degrees around the origin. Basically, we rotated the blue triangle 270 degrees. Now we calculate the coordinates of the triangle, this yellow triangle here. The A triple prime would be 2, -1. The B triple prime is 2, -3. And the C triple prime is 4, -1. So if we compare the first coordinates with these, we can see the rule. Here A is 1, 2, here is 2, -1. So we're flipping it and we're making this y coordinate negative. For the B is the same. We start with 3, 2 and we finish with 2, -3. So we flip this and we make the second coordinate negative, the y coordinate negative. And for the C is the same thing. We have 1, 4. Here we have 4, -1. We flip it and we make the y coordinate negative. So that will be the rule, right? We flip the x and the y. Here will be y, -x. And you see this one is negative. Now we're gonna see the rotation as a function. Basically, this R represents rotation. This E represents the center of rotation. This T is going to represent the angle of rotation. When this angle is positive, we're moving counterclockwise. When this angle is negative, we're moving clockwise. This ABC, this triangle ABC, represents the pre-image that is going to be rotated. And this triangle A prime, B prime, C prime represents the image obtained after the rotation. We're going to give an example here of how to use the protractor to actually calculate the resulting segment A prime, B prime after a rotation of this AB segment. Basically, E is the center of rotation. So we're gonna choose this point here for E. The coordinate 0 for the X, 1 for the Y, 0, 1. AB is gonna be the segment that we're gonna rotate. In this case, this segment here. So to rotate a segment 90 degrees, counterclockwise, because it's positive, we're gonna draw this dotted segment between this point A and the center of rotation E, and another dotted segment between this point B and the center of rotation E. Now we're gonna take our protractor and we're gonna align this segment here with blue dotted lines with this line here and this segment here. So you see we align the middle of the protractor, which is going to be the vertex of the angle, with the center of rotation E. Now we're going to measure 90 degrees because that's the rotation of this segment AB. So we measure from here to here is 90 degrees. We label this with a point. We remove the protractor. Now we calculate this distance here, which is 3.16. So if this segment is going to rotate 90 degrees counterclockwise, it's going to end up around here. So it's going to have the same distance, 3.16, and it's going to go across this point here that we calculated. So this will be a 90-degree angle. So we get the point A prime here. We rotated this point A 90 degrees and it ended up in this position here. Now we're going to do the same for this point B. Again, we always have to draw a segment between the center of rotation and the point that we're going to rotate. We put our protractor there, aligning the center rotation with the middle of the protractor. We measure the angle, which is 90 degrees. We mark this with a point. The distance of this segment is 1.4. Therefore, this distance from here in this direction is going to be 1.4 as well. Okay? So just so you understand, the distance in this direction is going to be 1.4. In this case, it coincides that the point that we use as a reference is the same as the point that gives us this distance. But sometimes that point doesn't give us the exact distance. Okay? So you have to make this segment longer or shorter, depending on the situation. So the point B prime would be here. Now we join both of them, and that's how we obtain the segment A prime B prime, which is a rotation of 90 degrees of this segment counterclockwise. So basically the point A was rotated 90 degrees. As you see, this is a 90 degree angle counterclockwise. And the point B was also rotated 90 degrees counterclockwise. So this animation shows what's going on here. So you see, basically we are rotating the segment 90 degrees counterclockwise. We rotated the point A first, and then we rotated the point B, both of them 90 degrees counterclockwise. In that way, we obtain the segment A prime B prime. B prime. So that will be all for this lesson. Thank you very much for the attention.